Nachmittag, meine Damen und Herren. Good afternoon, ladies and gentlemen. I welcome you to the Festival of Philosophy 2021 in Hannover. The first talk of this afternoon, the first discussion, is with Bruce Allen and Dennis Lehmkuhl on the topic, what do we know about the universe? Where does physics have its limits? Obviously in English. Bruce Allen, director at the Max Planck Institute for Gravitational Physics, head of the Division of Observational Relativity and Cosmology, is a honorary professor of physics at the Leibniz University Hannover and an adjunct professor of physics at the University of Wisconsin in Milwaukee, United States. His big work is on gravitational waves, and this latest has shown up the first detection of gravitational waves. He has been awarded with a lot of prizes together with his group. I only name 2017 the Bruno Rossi Prize of the American Astronomical Society, shared with the LIGO team. He will explain what LIGO means. And Dennis Lehmkuhl. Dennis Lehmkuhl is Lichtenberg Professor of History and Philosophy of Physics at the University of Bonn. His work focused on theories of gravity, space-time structure, and how they interact with matter. He has studied physics and philosophy in Oxford and Hamburg, and he is especially interested in Einstein's interpretation of general relativity and of other space-time theories, and on the question of how Einstein's positions square with the modern debates in the foundations of space-time theories. So, I leave it to you.
Thank you.
Thank you.
So I thought a good place to start our conversation today is with some basic things. You know, we're going to be talking about cosmology, black holes, general relativity, gravitational waves, and concepts which are abstract for most people, although they correspond to real things. And so this brings up the question, well, what is a real thing? Yeah. And I thought a nice place to start talking about this was just to talk about numbers, the integers, 1, 2, 3. I mean, if you think about it, these numbers represent things. You know, you say there's 3 cars parked outside. But actually, 3 is really an abstract concept. And if you go back at least a couple thousand years ago in philosophy, the notion is that concepts like that actually have a reality themselves. And so, just for myself, I can declare right from the beginning that I'm a believer in mathematical reality. I think, for example, that the number 3 exists without us. It's something that human beings discovered and not something that they invented. And I thought that would be a good place to start our conversation.
Yeah. Yeah, I think that's a very interesting question. And as you say, it goes back all the way, at least to the Greeks, probably much, much further, where we don't have written documents anymore. And I think different philosophers or different thinkers, right, the distinction between philosophy and physics is a relatively recent one. Different thinkers always had different positions and arguments for that.
I mean, so, natural philosophy, right, was the beginning of what philosophy was, and natural meant the world around us.
Exactly. And I think the important question about whether, say, the number 3 is real is exactly, it's a qualification that you had in your statement, namely, well, first is what does it mean for the number 3 to be real? And one common criterion, or something that's meant implicitly when somebody says, I believe the number 3 is real, is what you said explicitly, it's mind independent. It's something that exists independently of us. Whether they're human beings or not, the number 3 exists in a certain way.
But not all people agree on this. In my family, we actually have dinner table arguments about this because there's 4 of us, and 2 of us believe in this absolute existence, and others don't.
Yeah. And I think there's good reasons to disagree, right? I mean, in a way, it's the question, what are the necessary and or sufficient conditions for something to be real? And somebody might say, well, one necessary condition, maybe a sufficient condition, is that it can exist independently of minds. Somebody else might say, no, a necessary condition for something to be real is that it is material, right? That would make space and time, at least pre-general relativity, non-real.
And we're going to get exactly to that question of saying it's material. I mean, I guess if you go back in philosophy, you know, one idea is that things exist simply because we can think about them and visualize them. And I mean, you can think of simple examples like a triangle. You know, when you learned what a triangle was in school, the teacher drew some triangles on the board. And after they had drawn a few triangles, he said, I understand what a triangle is. It's 3 points joined by straight lines. But of course, the teacher never actually really drew a triangle. Because if you looked carefully at what they'd drawn on the board, the lines weren't straight, the points weren't. A true triangle as a mathematical object only exists in our mind. And so, the difference, I was taught as a kid that the difference between the natural sciences and philosophy was that in the natural sciences, we observe the universe, we do experiments, we draw inferences from that. And the question really is it the real world that comes first and then these ideas of ideal objects that come afterwards, or is it the other way around, or are they somehow intermingled?
Yeah. And I think one can find good reasons for either position, actually, right? I mean, you could think that in a way what the teacher is drawing on the board is a triangle, but it's not a perfect triangle. It's not what corresponds one-to-one to the mathematical concept of a triangle, because it has all these little deviations from a perfect triangle. And then the question is, well, what is that where it starts? All these triangles that we draw and that have something in common, and then we create the idea of a perfect triangle, and that's something we do, as you said. Or is it the other way around? The idea of the perfect triangle is already there in the Platonic heaven of ideas, and we sort of intuit that, and that helps us produce the triangles on the board. And I think one can defend either option.
I mean, I'm very convinced that mathematical objects exist and are things that we discover. And I mean, for example, the mathematician Paul Erdős, a great mathematician, was also apparently a very religious man. He believed in God, and he thought that God, of course, enjoyed mathematics and had a book. And in this book were proofs, the best proofs of all mathematical theorems. And so when Erdős saw a proof that he really liked, he'd say, that's from the book, meaning this is how God would have proved it. Yeah. I mean, to me, this is a very real thing. I was thinking, for example, a lot the past couple of months about a particular 9-dimensional space, a lattice, and a construction. I was constructing something in this space. This is a shape. It has 370 sides, which are 8-dimensional objects. These join on 12,704 faces that are 7-dimensional. And the connections between these things are things that I was thinking a lot about. Now, this is not an object, though, that exists out there in reality. The reality, at least, that we perceive is 3-dimensional in space and 1-dimensional in time. So you can't put a 9-dimensional object. Yet, for me, this is a very real thing. Yeah. So let's turn the question now to something that's like a bit less mathematical and a bit more real. Let's talk about electrons. We know that matter is composed, just ordinary matter, the gas, the air around us, the things in this room. They're composed of neutrons, protons, and electrons. The electrons are charged particles, and you learn in school that these orbit around the nucleus. So the question is, what is an electron? I mean, this is not something that we've ever directly perceived. It's too small, it's too light, we can't taste it, we can't see it, we can experiment. And in the experiments, you see they have certain behavior. You can describe these things by saying, well, there's a whole bunch of phenomena that I observe, and these can be explained if I think about this thing called an electron. But is there really such an object, or is this something that we've created to explain some phenomena?
Yeah. I mean, that also comes down to two positions that are, and it's still a hard-fought battle in the philosophy of science. So on the one hand, you have scientific realists who believe if our best theories of matter tell us that electrons exist, then they exist, right? We have to, in order to properly trust science, to take it seriously, if it says electrons exist, then that's what's the case. And anti-realists say, well, but we've never directly observed them, so we have to be careful. Maybe our concept of an electron is more a tool that we use to make predictions and that we use to make sense of phenomena and of data, and we shouldn't be too sure that what the theory says is there, is really there. And I think it's really not quite so easy to decide between the two, because even if you are a realist and you say, okay, I'm looking at modern particle physics, at quantum field theory, I've studied the equations, I understand what the theory says an electron is, and to what phenomena, what observations it relates. You can never be completely sure which parts of your understanding of an electron correspond to what it is in the real world, and which parts come from the mathematical tools that you use, from the formalism. You might have chosen a different formalism, and so that's difficult, right? So I find, for example, at the beginning of the history of quantum mechanics, 1925 to 1927, when Heisenberg and Born and Jordan developed matrix mechanics and Schrödinger developed wave mechanics, they both seem to be saying something quite different about the world, right? They said something very different about what is real. And it took a while to realize actually they're observationally equivalent, and there is a more fundamental formalism from which you can both derive them. But still, it wasn't quite clear which aspects of the quantum world were sort of put in by the mathematical formalism that could have been different, so different conventions, different tools used, and which ones really latched onto what is actually there.
And so when we talk about the reality of things, I mean, for me, an electron is a real object, so is the number 3.
Right.
But what we mean by that reality might be a little bit different than what the Greek philosophers meant 2,500 years ago. I mean, Aristotle, for example, thought that we should observe the world empirically about us and draw conclusions from this. And what he would think were real observable things, the change of seasons, the motion of stars in the sky, things like this, these are things which one could perceive directly with the senses and then draw inference from. But we have to now also give reality to things like subatomic particles that we can only perceive through some indirect chain of observation. And, you know, for example, people observing gravitational waves, which we'll talk about later, we don't see the gravitational waves with our eyes. We don't hear them with our ears. We see them through a set of instruments, which eventually result in pictures on a computer screen. So what we're really seeing is pictures on the computer screen and not the gravitational waves themselves. So we have to be very careful when we talk about the reality of objects to keep in mind that these objects might not quite be what we think of as normal objects.
Yeah.
So the notion of reality is perhaps a bit different. And I mean, an electron is a fine example because, for example, under certain circumstances, it doesn't travel the way a particle does. You know, if you have, for example, an experiment with 2 slits, the electron actually can pass through both of them simultaneously or together. It doesn't choose one or the other.
I don't think that necessarily means that the notion of reality has to be different. I think what it means to be real can mean the same thing for an electron, or possibly even for the number 3, as it does for a chair or a table. But for us to be sure that it is real, that's more difficult, right? We can make sure that a chair exists in a very direct, straightforward way. It's much more difficult to make sure that an electron exists as predicted by our theory, or that a gravitational wave exists as predicted by the theory. Partly, as you said, because there's so many intermediaries that we need to go through to get to the electron or to the gravitational waves. All kinds of instruments, all kinds of filters, often before we see something on the screen, right? And then the question is, I mean, you know much more about this than I, but which parts of what we see on the screen corresponds to the actual phenomenon, and which parts is a result of the instruments and of the filters and so on?
Yeah, I'd say that, you know, it all corresponds to the phenomenon. And that phenomenon is something.
But it could correspond to different aspects of the phenomenon, right?
Yes, absolutely.
Yeah.
And okay. So why don't we move our conversation in that direction? By the way, I'm at a bit of disadvantage because I don't actually know what the time is. We haven't arranged here to keep track of the time.
That's true.
Okay.
Okay.
But let's shift our conversation to some other objects. So we were talking about electrons, and you know, subatomic particles are a good example of something which does exist, but their existence has some aspects to it which are different than our ordinary reality. Let's talk now about much larger objects, which are black holes. Now, to me, one of the interesting things about black holes is that the idea for black holes, you know, we were talking about, do ideas come first or does nature come first, what we observe? And the idea for black holes actually stems back, I think, to the 18th century, to English and French mathematicians, scientists who were thinking about gravity. You know, Newton had discovered his universal law of gravitation at the end of the 17th century. And then by the 18th century, people were applying this. And one of the questions that was asked was, for example, if you have an object and you launch a mass, let's say a sphere, and you launch an object from it, it can climb up to a certain height. If I throw something in the air, it will go up a certain height and fall back down. If I throw it hard enough and there's no air friction, it will actually leave the Earth's gravitational field entirely. It would just go off and orbit away. And I think the escape velocity from the Earth is 11 kilometers a second. So if there's no air friction and I launch something straight up at 11 kilometers a second, it will actually make it out into space. It won't fall back down. And these scientists, they speculated. They knew how fast light traveled. And they speculated, and they said, well, if we make an object have enough mass and be small enough in size, then light wouldn't escape from the surface. Do you want to add something about the history of this?
Yes. So I think that those early speculations were, in a sense, the idea of a dark star, right? An object that would be so heavy that even light emitted at its surface could not escape its gravitational field and so would just fall down. And at the time, that idea made sense specifically because people thought of a particle theory of light. Right? Particles
corpuscular, right?
Corpuscular, yeah. A corpuscular theory of light. And then it's quite an easy idea. You think, well, light corpuscles probably has something like mass. Mass is influenced by gravitational fields. So if the gravitational field is strong enough, the light particle or the corpuscle should just fall back in. But then by the beginning of the early 20th century, things had shifted to a wave theory of light, right? And also to the idea that light waves wouldn't have mass, right? Until the beginning of the special theory of relativity, energy and mass were completely separate properties. And so I think this idea, something that was thinkable in the 18th century, the idea of a dark star, had become unthinkable, maybe not unthinkable, but something that if you thought about it, you would quickly think, no, that can't exist, or that wouldn't happen, because things had shifted. The concept of light had shifted. And so only once special relativity was there, and the idea was that mass and energy are in a sense equivalent. So even light waves that have energy would be influenced by gravitational fields. That was one of Einstein's earliest things that he emphasized as a consequence of such a theory.
And in fact, I mean, the first confirmation of Einstein's theory of general relativity was about 100 years ago when Eddington and his colleagues observed light being deflected, for example, as it passed near the sun.
Almost the earliest. In a way, the calculation of Mercury's perihelion was even before. But yeah,
okay.
Yeah. But yeah, so I mean, they were all very lucky in a way, right? That that solar eclipse happened then. Apparently, it was the best solar eclipse to observe something like this in at least 100 years. Since then, there was never again such a good solar eclipse.
And so people had this idea that objects moving at the speed of light couldn't escape when they were thinking of them as material particles. And then they somehow lost this when they started to think of light as a wave. But eventually this resurfaced.
Yes. And I think, but even when it resurfaced, there was a lot of opposition. And that was now because in the context of the new framework of the general theory of relativity, a dark star, or what we would later call a black hole, would have certain properties that many thought were anathema, that shouldn't be able to exist in nature. And Einstein in particular was very resistant. And it was conceptualized through a particular solution of Einstein's gravitational field equations, right? That if we have Einstein's new theory of gravity based on the Einstein field equations, every solution to these equations is in a way a possible universe or a possible part of a given universe. I can describe either universes as a whole or subsistence. And the first solution that described that was found was Schwarzschild solution. Do we have a
We have a picture of Schwarzschild, I believe. There's also a picture of Laplace.
Yeah, that's Laplace who came up with dark stars. And
so Einstein published his theory of relativity, his general theory of relativity, in November 1915. And I think within a few weeks after that, he received a postcard and then a manuscript from Karl Schwarzschild, who maybe was on the Russian front, I'm not sure. He was a soldier, I think, at that point.
Yeah.
And he found a solution, an exact solution to Einstein's equations, which is wonderfully simple, which we still study today, called the Schwarzschild solution.
Yeah. And for Einstein, that was a big surprise, because in his paper, also from 1915, November 1915, in which he predicted the path of Mercury around the sun, he had found a solution that had the properties of being spherically symmetric, like the sun, static, so it doesn't change in time, and so-called asymptotically flat. The gravitational field peters out the further away you move from the sun. And Einstein found this solution as an approximation of the real equations. It was an approximate solution. And he actually thought at the time that nobody would ever find an exact solution because the equations were just too complicated. Mm-hmm. And so it was a big surprise to him when Schwarze wrote to him and said, I found the exact counterpart to your Mercury solution that describes the gravitational field of a star.
But Schwarzschild's solution had this interesting thing in it. It had two types of what mathematicians call singularities. There was points when the equations broke down. And one of those occurs at what we now call the horizon of a black hole. And this is now believed to be what's called a coordinate singularity. It's known to be a coordinate singularity. And that singularity was a problem for Einstein. Einstein thought that this meant that the solution was mathematically correct but didn't describe the physical universe.
It didn't describe the universe as a whole. He was perfectly fine with using the solution to describe the exterior gravitational field of a star.
The exterior means though away from this singularity, right?
Yeah, so he was fine. Everything that was outside of what we now call the horizon, he thought is very important, very good. But once we reach what we today call the horizon, he thought there's a mathematical artifact, something that does not correspond to reality, and so we have to cut off the solution at that point.
That's right. Yeah. And this actually, I think, was really only clarified after Einstein's death. I mean, during the period, Schwarzschild's solution dates back to 1916, but then in the decades that followed it, it was studied by scientists and mathematicians, but I think the real full understanding actually only came soon after Einstein died, when it was discovered that actually these apparent problems that took place at the horizon were actually simply a mathematical artifact, that in fact one could write down the solution in other ways where the behavior at this surface called the horizon was perfectly normal and regular.
Mm-hmm. That's true. But I think something more happened there, because these types of coordinate systems where you can transform away the singularity at the horizon, or the singular behavior at the horizon, already were known to some people in the 1920s, in the 30s and 40s. Eddington found such a coordinate system, then Lemaitre and Robertson found such coordinate systems, and then Finkelstein in the 50s rediscovered Eddington. So in a way, the knowledge to make that step was there, but nobody quite made that step. Mm-hmm. So I think what was needed, and I think there's a real shift, a real, a second relativity revolution in the 50s and 60s, when people like Penrose and Finkelstein and Rindler and so on start to think about global structures and general relativity. And only then can the concept of an event horizon really emerge, because it's a global feature of a given space-time. And so I think in a way it wasn't that all Einstein and all the earlier people that they didn't get it. They missed out. They didn't have the right methods, the right conceptual, the right mathematical ideas that would really allow to turn the Schwarzschild solution around and understand it in a new way.
And so when I was an undergraduate student in the 1970s, and when I was a graduate student in the early 1980s, people would still discuss whether black holes could be found in nature.
Right.
This was still an active discussion. Were these real objects? And for example, there were systems, binary systems, that had been observed where what we know now is that there's a black hole next to a star, and the black hole is actually sucking matter off the star. It's falling onto the star and it's radiating X-rays. Mm-hmm. And these systems had been studied, and there was a lot of evidence that, for example, from measuring the speeds of the gas as it fell in and from the temperatures, that there was an object at the center that was very small, and was probably a black hole. But I think at that point, the evidence wasn't conclusive. Mm-hmm. But now we go ahead, 40 years later, and we have a lot of knowledge about black holes and their real existence in our universe. And I think one of the results that's come out during the past year, it's a picture here. This is a very famous picture made by the Event Horizon Telescope, which shows a black hole in the galaxy M87. That's Messier Object 87, long known to astronomers. And what you're actually seeing here is light that's coming from matter, which is orbiting a black hole. This is a very, very large black hole. It's something like 6 times 10 to the 9 solar masses, so it's almost 10 billion times as massive as our sun. And this object is at a distance, I think it's about 15 megaparsecs roughly. It's in the Virgo cluster of galaxies. And this picture is quite amazing because it was made by combining data from radio telescopes located basically as far apart on the Earth as you can get, operating at very high frequencies. And the remarkable thing is that at the center of this object, there's a black hole which, you know, for light to travel a distance equivalent to the size of this black hole would take a few hours. And what we're seeing in this image, that black thing in the middle there is the area around the horizon of the black hole, which is located at the center. It's quite a remarkable photograph.
It is. But do you think, I mean, we know that the photograph is the amalgamation of a lot of data and a lot of photographs and reconstructions. Do you think with the data from the Event Horizon Telescope, with LIGO, and also with the data from how how stars move around the centers of galaxies, can we be absolutely sure now that black holes exist?
I think we can be absolutely sure that black holes exist. This I'm sure of. This, to me, they exist in the same way that the number 3 exists.
Right.
Okay? Yeah. I'm absolutely convinced of their existence. What I would say, though, is also the case is that we don't quite understand entirely what they are. Mm-hmm. Because, for example, they contain features. So we talked about this apparent singularity at the horizon, which we now know is not a singularity. It is a surface of no return because nothing can go faster than light. Mm-hmm. So back when Laplace and Mitchell, for example, were studying these dark stars, they didn't know that things couldn't go faster than light. So they could imagine, for example, that even though something going at the speed of light couldn't escape from the star, perhaps something going faster could. Mm-hmm. But we now know that nothing escapes from a black hole. And the matter that falls inside the event horizon, what happens is that for that matter, the direction of time and space reverse. Mm-hmm. So for example, you and I can move forward in time. Mm-hmm. We get older, but we don't get younger. And we can move in all space directions. But when you get inside a black hole, the directions of time and space reverse, and you end up getting carried into this thing called the singularity.
Right.
We don't understand that aspect.
Right.
So I believe in the existence of black holes, but I don't believe that we understand them completely.
Right. But I want to come back to the idea, to the question of in what way they exist. So you say you believe in them in the same way that you believe in the number 3, in a way that makes it easy, right, for you, right? Because if you're already a mathematical Platonist, you believe in the existence of mathematical objects, then you also believe in the existence of all solutions to Einstein's equations in a way. They're all mathematical objects that correspond to something real, right? But there are some that correspond in a different way, right? Some
you find in nature and some you don't.
Yeah, exactly.
Yes.
So that's so it could be that black holes exist as mathematical objects, as solutions to the Einstein equations, just like the Gödel solution to the Einstein equations exists, even though it doesn't seem to relate to our universe. So they can we be sure that they exist in our universe?
I am certainly convinced that they do exist in our universe, and that we've observed them on a very regular basis.
I'm convinced too, but the question is, can we be sure?
It's a good question.
Yeah.
I think if we could answer that question, we'd have less to talk about today.
Yes, that's true. Yeah.
How are we doing for time?
There's a clock over there, actually.
Oh, very nice. Okay, so fine.
Yeah.
What should we talk about next?
Well, maybe we can talk about, say, the counterpart collaboration. So this is the Event Horizon Telescope that made that picture. And you yourself are heavily involved with the, well, even bigger collaboration that also discovered black holes first, actually, by, or that's how the results are interpreted, by discovering the gravitational waves that are emitted from 2 black holes that oscillated and merged and then emitted gravitational waves. Okay. So maybe we can talk about this. Yeah.
So I think the viewers here can see now a picture of the LIGO instrument. This is the Laser Interferometer Gravitational Observatory. This is one of 2 gravitational wave detectors in the United States. There's some similar detectors in Europe, in Germany, and in Italy. And this made the first detection of gravitational waves in September 2015. I was part of that discovery, and it's kind of one of the scientific highlights of my career, and was a very important moment for me. These instruments, what they do, so let's just say a little bit about gravitational waves. So Einstein's general theory of relativity is a theory of gravity, which replaced Newton's theory. Newton's theory of gravity, Newton's universal law of gravitation, has a problem, which is that in Newton's theory, gravitational forces act instantaneously. And this violates Einstein's theory of special relativity, which says that nothing can go faster than the speed of light. And Einstein's theory is a replacement for Newton's theory of gravity, and it makes some interesting predictions. And one of the predictions it makes is that if you take two massive objects, my hands, for example, and you accelerate them, you actually produce ripples in the curvature of space-time. And these ripples travel away at the speed of light, carrying energy and momentum with them. And these are called gravitational waves. And to observe these, the easiest way of thinking about how to observe these is you just take a couple of objects floating in empty space. And when a gravitational wave passes by, these objects kind of bob up and down a little bit. Now, it's tricky to say that because Einstein's theory is a theory which is independent of coordinates. And when we talk about motion, we already imply something about coordinates. In these instruments that you saw a picture of, what happens is light travels back and forth between mirrors. The mirrors are hanging from wires, so they're free to move, kind of like objects floating in space. They're floating in 2 dimensions. And when a gravitational wave goes by, what happens is that the distance between these objects changes slightly, very slightly. And we measure that distance with lasers. And what we saw, there's a cover here I think we can show the viewers of Physical Review Letters, which shows the discovery observation. What you see on the top of this is 2 black holes. There's a kind of cartoon showing them orbiting, first far away and then closer together. And what happens is these 2 black holes, as they orbited and merged, we saw the last perhaps 5 or 6 orbits of this system. And as they orbited and merged, these black holes twisted a little bit the geometry of space-time. And those twists traveled away at the speed of light, and they reached us tens of millions of years later. And what's seen on the bottom of this picture is in red and now in green are the waveforms. So this is the motion, the length between the mirrors of this detector changing. And this is about roughly 1/4 of a second of data. And the horizontal axis is time. And the data comes from 2 instruments that are separated by about 3,000 kilometers. So what happened is that the signal actually arrived first at the detector, which was in Livingston, Louisiana, and then it arrived roughly 7 milliseconds later at the other instrument. So these 2 waveforms have been shifted from each other by 7 milliseconds. And what we're actually seeing here, as these 2 objects orbit each other, each orbit produces 2 cycles of gravitational waves. So you're seeing here the last 4 orbits of 2 extremely massive black holes just before they merge to form a single black hole. It's quite a remarkable picture. And I can say more about this, but let me hand over to you for a minute and let's go back and forth.
I just want to ask you a few questions about this. So one is that when you described, well, first of all, one thing that I find particularly interesting about the whole scenario is that there's no, in contrast to Schwarzschild's solution, there's no exact solution to Einstein's equation that describes this, right? There's no exact solution that describes...
Oh, there is an exact solution, we just don't know what it is.
Fair enough. Yes. But that creates a lot of work, right? The fact that we don't know that solution. In fact, we don't know that it exists, right? Well, there's neither an existence nor a non-existence proof.
So people have, many people have taken Einstein's equations, put them on computers and solved them.
Yeah.
And when you do this, you actually can find solutions to Einstein's equations which are extremely close to what we've observed. In fact, they're so close that, roughly speaking, we can't tell the difference between our observations and the computer simulations. Yeah. Yeah. By the way, this is a remarkable thing. I mean, Einstein really didn't believe in the Schwarzschild solution. I think he didn't really believe in black holes.
Great.
And he also, by the way, thought that gravitational waves were going to be too weak to ever be observed. He did an estimate of how much energy would be emitted, for example. And so, yet we've observed something with instruments which is predicted by Einstein's theory, and yet he himself probably would not have imagined that this could be done.
I think even more. I mean, when he predicted the when he predicted gravitational waves in 1916 and then in an improved paper in 1918, it was again as solutions to the linearized Einstein equations, so the approximate equations. And then in the 1930s, he worried whether these approximate solutions actually correspond to an exact solution of the full Einstein equation. So he actively, for a while, thought, oh my, they are an artifact of the linearization. They don't really exist. They only exist in that limit that doesn't really correspond to reality. And so for a while, he really was convinced that gravitational waves don't exist at all. And then that turned around again, and he realized that there are actually exact gravitational wave solutions. But so one question I had about was when you said one element of this is that the gravitational waves that are emitted by the two black holes and in the merging process, they carry momentum and energy away. And of course, you have that in the mathematical description of what happens there. But one thing I wonder about is, in the way that the LIGO detectors work and how you give an account of how the mirrors move when the gravitational wave hits, do you need to assume that they carry energy and momentum, or could you also just describe everything that the detector does without drawing on those concepts?
It has to be that these waves carry some energy, because you see, because the mirrors actually do move. I mean, if you have a damping in there which takes energy away, it actually gets, we can't measure that energy, it's too small.
Right.
But everything we believe right now about physics says that yes, these waves carry energy and actually transfer a very small amount of it to our instrument.
Yeah.
The trouble is the cross-section for that, the amount of energy that gets transferred is really tiny. It's one of the reasons why gravitational waves are so hard to detect.
Right. But when you describe what the detector does, do you need to draw on these concepts, or can you just say, well, the gravitational wave hits, so the natural paths of space-time, the structure of space-time changes in the vicinity, the geodesics, and that's what makes the mirrors move, the geodesic deviation.
You can even describe it that the mirrors don't move, it's just that the frequency of the light inside changes. But nevertheless, I think it is clear from studying the system that energy is being lost to it. And you know, this system consisted of two black holes. One was about 30 solar masses, the other was about 35. And in the process of merging, these systems emitted something like 2 solar masses worth of energy. I mean, it's remarkable. During our lifetime, our sun it's undergoing thermonuclear burning. It's turning lighter elements, hydrogen, into heavier ones, helium. And this process goes on for billions of years. And during that entire time, our sun loses perhaps 1% of its mass.
Yeah.
And here we have a system which lost, in a fraction of a second, several hundred times that amount of energy.
Yeah, I agree that that's mind-boggling. And and I'm not doubting that analysis. I was just curious which parts of the properties that correspond to the original system that emits the wave and the things that you know from there actually are needed in the analysis of what the detector does, right?
In the analysis of what the detector does, I mean, there's two parts. One is, how does the detector function as an instrument? And this is an instrument which was built by a large group of people over many years. And as you build something like that, you poke at it. You experiment with it. You try out different parts. And for example, one of the things we did was what are called hardware injections. This is where you displace the mirrors a little bit by applying forces to them. The forces can be applied in a couple of different ways. One is, we treat one of these mirrors as a piece of a capacitor and push it with a little bit of electrical charge. Another way we can do it is we can push them by bouncing light off the back of them. And so by actually moving the mirrors of the instrument, we can study how the instrument works. So in this sense, we can experiment directly with the instrument. But then when something arrives from the outside, in this case a gravitational wave, there all we can do is observe how does the instrument react to that. And for doing that, we really don't need much information. We get it directly from the instrument itself. So the whole modeling process is only useful because, so that waveform lasted about less than a quarter of a second. But for an expert in this area, somebody who studied it, it takes less than a quarter of a second to say, that's 2 black holes.
Right.
And maybe I'll explain that. You see, if you look at normal physical systems, a mass on a spring, for example, which oscillates, typically something which goes into oscillation it oscillates at a fixed frequency, and it loses energy, it gets damped by the surroundings and slows down. So if we observe something like that, we see a signal which is sinusoidal, and it gets weaker with time. This signal that we see here has two properties that are different. One is that the frequency is increasing with time. It's not decreasing. It's not constant. It's not a constant frequency. And the second thing is that the amplitude is not getting smaller. It's getting bigger. So this is an unstable system. It's somehow the motion inside it is occurring faster and faster, and it's getting more and more extreme. This is exactly what you see when two objects orbit each other and they emit gravitational waves. And by the way, these are black holes. People sometimes say, well, a black hole can't emit anything, right? How can it emit gravitational waves? And an interesting thing here is it's not the black holes that are emitting the gravitational waves. It's the interaction between the two black holes orbiting each other. That's perturbing space-time, and that's the source of the energy. And the black holes falling together is actually what's releasing the energy.
So it's not that the black holes come from the insides of the black holes, which is supposed not to be possible to escape.
That's right. So the gravitational waves are not coming from inside, they're coming here from outside.
Yeah.
And an interesting thing is that if you look at how the frequency is changing with time, there's a plot here now which shows a curve. It's a kind of a colored blue curve. I think it's probably the next, that's it. This shows the same data, but now what you see on the horizontal axis is time, and on the vertical axis is frequency. And you can see the frequency is increasing. This is the speeding up that we saw before. If you simply look at how this frequency is changing with time, those white lines there show the slope, how quickly frequency is changing with time at several different moments. From that, you can very easily determine that the masses, which are orbiting each other, are about 30 solar masses. And you see, you can also determine how long they're taking to go around each other from seeing what the time is between the different cycles of waves. Those two things tell us already that these objects are only a few hundred kilometers apart.
Right.
And so they can't be, for example, ordinary stars.
Yeah. But you said a few minutes ago that if an expert looks at the waveform, they immediately see that these are two black holes that orbit and eventually merge. But this, I mean, the first time we saw such a picture is only 6 years ago, right? So when that happened, when LIGO had only just been turned on, and the first signal that turned out to be the big merger of 2015, when that was seen, what kind of process was there to establish, yes, it must be a black hole, there can't be any other explanation for the signal that we've just found? Because there was never before such a signal, right?
That's right. So first of all, we knew what such signals would look like because people had solved Einstein's equations approximately and with computers and already studied such systems. Yeah. So it's true that this is the first time that we'd seen such a signal in nature, but it's not the first time that we'd seen such a thing on our computer screen.
Right.
But the question of how we knew that this was real, this was really a big issue for us because the first detection of gravitational waves was actually announced in the late 1960s and the early 1970s. It turned out to be something that could not be repeated, and we now believe there's no possible explanation for this other than error. Yeah. But this meant that we needed to be particularly careful. We needed to rule out other possibilities because the scientific world had already been misled once about the discovery of gravitational waves, and we couldn't afford to do that a second time. For me, there was an important moment in understanding whether this was real, and I think there's another drawing which shows this. This is the first of two, and let me explain what this is before we show the second one. So within a couple of days after this observation, I had taken the data and I'd done an experiment, which is I'd plotted this data in time and in frequency. And here the horizontal axis that you can see is time. And what I did is, and one of these plots on the left is the data in Hanford, and the other is on the right. And those sort of colored blobs that you see on the right-hand side of each of those two plots is the actual data from Hanford and from Livingston. On the left-hand side, 0.6 of a second earlier, is a simulated signal that I added in to the data. I just added it in to see how this looked. And you'll notice how very similar these things look. They look slightly different because the noise in the instrument 0.6 of a second before was different. And then I did the following experiment. I tried shifting my signal, which I'd added in, 0.6 of a second later, so that it coincided with the actual signal. And I also changed the sign. I inverted it, so that instead of adding to the signal, it should subtract. And if we can flip to the next picture, that's what happened. It completely disappeared. The signal that we've observed matched what would be expected from two black holes so well that it simply disappeared like that. For me, that was one of the key moments. After that, my main worry was that this was actually not a mistake, but it was actually fraud.
Because it fitted almost too well.
It fitted very well, and you know, perhaps somebody could have snuck a signal into the data. And we were actually concerned enough about that, for example, the electronic cabinets where the detection electronics sits were actually locked. They were actually locked and sealed, and when we finished our observing run, these were actually opened. We wanted to make sure that nobody had stuck an iPod Nano in there with a waveform. There was other ways that we were able to check this later, which we can talk about if we have time. And we have made further observations since that time, which are really quite conclusive because we see sources not just with gravitational waves. But at the time, my biggest concern was really that this was somehow a mistake that was a deliberate one, but that's not the case.
Right. One other question I had about this was that, I mean, before you see the waveform that we saw on the cover of the Physical Review letters and so on, you need to use gravitational wave templates to basically filter the raw data, right? So it's a bit like you filtering out all the stuff that is sort of noise and that disturbs. And how worried are you about this? And how worried is the collaboration that there could be a version of, you see what you expect by filtering the data in this way?
One of the interesting things, so this signal was actually first seen by a human being here in Hannover, Germany. It was a postdoc in my group who was working on a data analysis pipeline called coherent wave burst. And this is actually a pipeline that is designed to look for signals where we don't know how it behaves in time.
Right.
This was actually something which was designed simply to detect things that go bump in the night, something that produces a waveform that we hadn't expected. Now, this is a type of waveform that we did look for deliberately, but that's not how we first found it. So I think that's kind of a conclusive answer to your first question.
Right.
We didn't find this specifically because we were looking for it. It was actually detected with a very generic analysis system that just looks for things that generate unusual peaks.
Right, right. Another question I had was that, so these are the observations from 2015, binary black hole merger. And then in 2017, there was another highlight when the first binary neutron star merger was observed. And in a way, to some extent, that was, I mean, in a way, nothing beats the first discovery of a gravitational wave. But in a certain sense, it was even more exciting because you could observe both the emitted gravitational wave and the emitted electromagnetic wave, the light signal that was emitted, and they arrived on Earth within 2 microseconds of each other.
2 seconds.
2 seconds.
It's 1.7 seconds delay.
Yeah. But very, very close, right? And even that could be accounted for because the electromagnetic wave was supposed to be emitted a little bit after, given the model. And that excluded a whole barrage of previous alternative theories of gravity that were rivals of GR and that finally were as experimentally directly falsified as anything ever was, arguably, right? So how?
So let's talk about this a bit. So first of all, neutron stars. So what we've been talking about until now was the first observations made by LIGO in September 2015 of the merger of 2 massive black holes. And subsequently, the instruments saw another roughly dozen such events. They were at different distances from us with different masses, but they were 2 black holes merging together. Now, there's another type of very heavy but compact object in the universe called neutron stars. And by the way, neutron stars are interesting objects also in the sense that they too were conceived of before they were discovered.
Right.
In the 1930s, I believe, very soon after the discovery of the neutron, Bade and Zwicky propose that there may be objects left behind after supernova, which are composed of neutrons. Now, this is very interesting. If you look at an atomic nucleus, just an ordinary material, iron, carbon, this is composed of a nucleus which is made of protons and neutrons, then surrounded by a cloud of electrons. And the cloud of electrons is roughly 10 to the minus 8 centimeters in size. The nucleus inside is much smaller. It's 100,000 times smaller, 10 to the minus 13 centimeters in size. And the idea that Bari and Zwicky had was that after a star had burned up its nuclear fuel, stars are big balls of gas, and they're supported against gravitational collapse by the thermonuclear burning that takes place inside them. And when that ends, gravitational forces can pull the whole star together. And they had the idea that perhaps what's left behind after this is an object composed of neutrons, which is like an atomic nucleus, but much, much bigger, heavier than our sun.
Because there's no repulsion, it can be very small.
Indeed.
Right?
And these objects are roughly, the size of an atom is about 10 to the minus 8 centimeters. The size of a nucleus is about 10 to the minus 13. It's 5 orders of magnitude difference. If you cube that, you get 10 to the 15. And that's roughly the difference in density between a neutron star and ordinary matter. So if you took, for example, a mountain on Earth, which is a kilometer by a kilometer by a kilometer, that's 10 to the 5 centimeters in each direction, you crushed it in all directions by 5 orders of magnitude, you would produce something of this kind of density. And these objects were found in the late 1960s, rather unexpectedly and surreptitiously, and they're now well studied. We have several thousand neutron stars that have been discovered because they're radio pulsars. We think our galaxy contains something like 100 million of these objects. And some of these neutron stars are found in binary systems where they orbit each other, but with orbital periods of hours. And we actually knew about the existence of gravitational waves by studying a system composed of 2 such orbiting neutron stars long before the LIGO detections were made. But we didn't observe the gravitational waves directly, only through their indirect consequences. So in August 2017, LIGO observed another gravitational wave signal, which was unlike the ones that we had seen before. And the reason it was different was, first of all, because the frequency was changing much more slowly. In the wave that you saw, there was only about perhaps 10 or 12 cycles. And during this time, the frequency evolved from a low frequency to a high frequency. This other signal that was seen lasted much longer. And by the way, it's weaker. You can't see it in the data. You can only see it through mathematical analysis. But that corresponds exactly to the signal that's produced when 2 neutron stars orbit each other very close together and merge. And we think that this happens in our galaxy about once every 10,000 years. And this merger was not observed in our galaxy. It was observed in another galaxy. But if you go through the pictures, the last one here shows 3 things. Let me describe this. The blue plot in the middle with all the colored dots and so on, the light blue curve there shows the gravitational wave signal sweeping through frequency, starting out at low frequency and going to a higher frequency. And where that light blue line disappears off the plot, that's about the time that the 2 neutron stars merged together. And when they did, they formed a black hole. Now, what you can see in the upper and lower plots are some observations made by the gamma ray burst monitor on board the Fermi satellite and a collection of detectors called Integral. What was observed 1.7 seconds later was a burst of gamma rays. That burst of gamma rays came because as these 2 neutron stars merged together, some neutron-dense matter got squirted out and then decayed. It's an incredibly catastrophic event. Remarkably, 11 hours later, astronomers from SWOPE found a flash of light, and you can see that on the right-hand diagram. So the LIGO and Virgo observations constrained the source of these gravitational waves to a rather narrow region in the sky. I believe it's the green ellipses that are shown there. And the Fermi observations of the gamma ray burst also constrained the observation. And I think that's probably the bluish circle there. What happened is that optical astronomers started searching the sky, and they discovered a burst of light. And there's two pictures there. I think one of them was taken roughly 20 days before this event, and one was taken 11 hours after. And if you look, you can see by the cross there, there's a, I wouldn't call it a new star, I'd just say a new burst of light that emerged. So this is really the ultimate proof that the gravitational wave detectors work as we thought, because this gravitational wave event was accompanied by another one. Yeah. Now, an interesting question is, why did the light come 1.7 seconds later? After all, gravitational waves and electromagnetic waves are supposed to travel at the speed of light. Mm-hmm. But in fact, these electromagnetic waves were not emitted at the exact moment of the merger. They were emitted sometime after by the matter that was left behind.
So, I mean, all these results together, and I mean, all the observations of the last 6 years, taken together, it's significantly more experimental data about, you know, testing general relativity than at any point in the previous 100 years, right? So how has that influenced you? I mean, were you always sure that general relativity is the right theory of gravity? Are you more sure now, or do you think there's still room for alternatives?
I am literally a card-carrying member of the General Relativity Society. so in this sense, yes, I am a believer in Einstein's theory. Of course, we should only believe in things because we have empirical evidence for them. And Einstein's theory had, you know, previously made predictions. One of the first was maybe a post-diction. It was an explanation for the anomalous precession in the perihelion of Mercury. The orbit of Mercury is an ellipse which rotates in a way that couldn't be explained. Einstein's theory explained this. It made other predictions. It explains how light bends as it passes near the sun. Other ways of calculating that give a result which is a factor of 2 too small. Yeah. It made other explanations which could also be, it explained other phenomena which could also be tested. So Einstein's general theory of relativity was already a well-tested theory before we made our observations. But our observations let us test it in a way that it couldn't be tested before because...
And in the strong field regime.
That's right. Yeah. So perhaps we should explain what we mean by that. When light passes by the sun, it's deflected a very small amount. It's such a small amount, it's very difficult to measure, and this is why expeditions with special equipment and tools were necessary to do this in 1919. Now, if light passes, if you take a black hole which has the same mass as the sun, and you let light pass by it, let's say, 1 million kilometers away, that's roughly the size of the sun, it will bend the same amount that light passing by our sun does. On the other hand, if the light beam passes by at a distance which is a few times the Schwarzschild radius, so for the sun this would correspond to a few kilometers away, the light will actually not be deflected a little bit, it will actually bend a lot. And if the light actually comes closer, it can actually go into orbit around the black hole. So it actually never leaves. It can fall in or it can go into orbit. So we are testing now, with the observations that are made of gravitational waves, we're actually testing general relativity when these objects get so close together that light, if it were emitted, would actually orbit around the system a few times before it escapes to us. And at the very end of our observations, we're actually seeing the black holes merging. So this does give us a test of general relativity in the strong field limit, where the effects of relativity are extremely large. And so far, again, Einstein's theory has passed all of these tests beautifully. Mm.
And it is also, that brings us back in a way to the beginning. It's the mathematically simplest option that there is, right? I mean, other theories of gravity, rivals of GR, were proposed, especially since the 1950s and 60s. And GR stands out among those as mathematically by far the simplest, and in a way the most beautiful.
Well, so this brings us now to an interesting question in physics, which is, and maybe this also brings us back to some of our earlier discussion, which is, you know, what does it mean to explain something? So I was interviewed before this discussion, and the reporter who interviewed me, he asked me a question. He said, well, do you understand quantum mechanics? And I said, well, you know, what does it mean to understand something? In in physics, we take sometimes a very pedestrian point of view. We say to understand something means that we can explain. It means that we can predict what will happen. So you give me a certain situation and I can predict successfully the outcome before you've done it. That's one notion of understanding, but it's not a very satisfying one. Because it means if I just give you a box that has some gears and wheels that you can turn, you can put stuff in and turn the wheels and out pops the answer, but we haven't really understood it.
Yeah. But I feel that sometimes when people ask that question, they ask for a very particular way of understanding, as that in German you would call anschauliches. You know, you can intuit, you can picture it. And of course, maybe that's too much to ask, right? That's too much to ask of understanding.
But for me, this is, for example, my understanding of general relativity is actually, it's a geometric theory, and it's actually based on geometry.
Yeah.
And so, you know, this notion of seeing something as being a form of understanding, I actually think, you know, words like insight, for example, in English, and I'm sure in many other languages, have a lot to do with vision as a way of understanding. But, you know, if we
shouldn't
take...
demand it's the only way to understand something, right?
I'm always afraid to say that there's only one way to do anything.
Yeah.
I mean, everything in my education has taught me that there's many ways often to arrive at the same answer. It's one of the things I love about mathematics, is that given a well-posed problem, you can often find the answer in many different ways, but they all agree with each other. And, you know, Einstein's theory of relativity explains, for example, gravitational waves. It explains modern cosmology, the Big Bang, but it explains it in terms of some other concepts. Now, why should that be the way that the universe really is? Why should it be that mass and energy curve the geometry of space-time and objects move in a certain way? We can explain that in terms of, say, some action principles, but why those happen to describe our universe, we don't know. So ultimately, can we expect that we will get an understanding, or is this a philosophically
I mean, there are a lot of philosophers and
unanswerable question?
I don't know. I mean, there are a lot of philosophers and a lot of physicists who believe that there ought to be an answer to these questions, right? Why is the universe that we live in the way it is? Why is it these laws? Why do the constants of nature have these values and so on? And related to that are multiverse and Anthropic Principle considerations. I've never felt the pull of that. I feel this is one universe. This is one way the universe could be. It happens to be the way that we live in. There could be other universes with different laws of nature, or the same laws of nature but different values for the constants of nature. And I think I am quite happy, actually, just to understand the laws to some extent that govern this universe, even if I don't know where they come from and why they are as they are.
I'm quite happy to stick to this universe only because for me the universe means everything that we can measure and possibly experience. So a multiverse, if there's other universes but we have no access to them, to me this denies their existence. Although again, if we go back to the notion of what existence means, perhaps that's not really the right way of thinking about it. But even within our own universe, you know, why things are the way they are is really a big question. I mean, for example, we know that the universe is described not with classical mechanics, but with quantum mechanics. It's very interesting, for example, from the point of view of questions like free will. Newton, when he was studying physics, he thought that, for example, you could specify the positions and the velocities of all objects, and if you did that, and you understood how these objects interacted with each other, you could predict the future. If that's really true, and if we were such objects, it would make it very difficult to explain things like free will. How can you choose?
Illusion.
It could be an illusion. And of course, this is a philosophical question which has been addressed over the years. I personally find that hard to swallow. And you know, quantum mechanics may offer a way out of this, because quantum mechanics says that in fact, you can specify the initial state of a system as well as possible. Even so, you cannot predict the outcome exactly. You can only make statistical inferences about it. So,
yeah, although I would say that's already part of the interpretation of quantum mechanics rather than the quantum mechanical formalism itself. The formalism by itself is deterministic, right? The Schrödinger equation is a deterministic equation. It's via the interpretation of, the wave function via the Born rule that we related to probabilities in our universe. And so there's already, I think there is a bit of leeway there. I'm not sure whether there is a clear path out of the whole free will debacle using quantum mechanics, because to the extent that there is a path, it rests on a particular feature of the interpretation of quantum mechanics rather than on the formalism itself. Yeah.
Indeed.
Yeah.
I wonder if this is a good place for us to stop, or should we continue? I mean, there's some other things we can talk about if we want to. We can talk about cosmology, for example, about the Big Bang. Would this be an interesting topic for a few minutes?
Or should we stop and other questions in the chat, or should we go on with cosmology? Okay, so we'll talk about cosmology for a moment. Or?
You go first.
Okay. So one thing that I find very interesting is, nowadays the idea that the universe started in a Big Bang and that it had a beginning has become very commonplace, even in popular culture, right? It's the kind of idea that I feel that almost everybody finds sort of obvious already nowadays, right? And I mean, I don't know, maybe
it's a very unobvious thing, isn't it?
It's an unobvious thing when it started, but it has become very absorbed in popular culture. So, and when it first came about, most physicists, or many at least, thought the universe would be eternal, right? That it didn't have a beginning.
And indeed, I mean, if you go back to Newton and even Einstein at the beginning of the 20th century, people thought of the universe as a very static place.
Yeah.
When we observe it, yes, we see the stars going by in the sky because we know the Earth is turning, we know the Earth is orbiting the sun, and so we also see things changing. But this change is just due to our local motion, and people thought that the universe beyond us was a very static place, and in fact had probably simply existed forever because there was no sign that there was any beginning or end to it. But then, in the 1920s and 1930s, the astronomer Hubble made an interesting discovery, which was that the universe was getting larger, that things were moving apart from each other. And then in the 1960s, a remnant of radiation called the background radiation was discovered, which was demonstration that the universe had once been very small and hot. In other words, Hubble saw things moving away from each other. If you extrapolate backwards in time, about 14 billion years, all of that stuff was together. And when it was together, the universe was a lot hotter, a lot smaller, and the radiation left over from that phase is visible to us today. It's actually been studied now in great detail. So those are, let's say, two of the pillars of modern cosmology. The last one is the fact that we can predict what the abundances of the different light elements are, because the light elements were formed during the first 2 or 3 minutes after the Big Bang. So we actually have a very clear picture of what happened starting within seconds after the beginning of the universe.
Yeah. One thing that you mentioned, I feel, is sometimes not appreciated enough, namely that, in a way, it was really only the discovery of the cosmic microwave background that really sealed the deal, right? Until then, since Hubble, we knew the universe was expanding, but that was compatible with it having been sort of not always having been expanding, right?
There was other evidence to the contrary. For example, the numbers of radio sources as a function of their amplitude was some indication that the steady-state universe model was wrong.
Yeah.
But I still find this model of the universe was a model in which the universe was always expanding, and there was always new matter being generated to produce it. It's kind of remarkable to go back now and read these papers, because, for example, these papers suggest that, well, every now and then a hydrogen atom just pops into existence from nowhere.
Yeah.
And we read this now, and to me it seems kind of strange.
But this is what I find interesting. What kind of hypothesis or what kind of idea appears strange and which appears natural at a given point in historical development, right? And I think at the time, at least for the people who propagated the steady-state theory, the idea of a Big Bang, the beginning of a universe, felt like a way more unnatural hypothesis than the idea of continuous creation of matter. versus nowadays. That's exactly what I mean. It's clearly the other way around, right? The idea of a Big Bang is exciting, but it's not something that we sort of shy away from anymore.
That's right.
And back then, at least for many physicists, it was the other way around.
And you know, the modern mathematical description, so models like our universe are described by a solution of Einstein's equations called the Robertson-Walker metrics. And we can study the properties of, let's say, the singularity, what happened at the beginning. And one of the things that many people don't realize is, you know, Hubble saw that everything is moving away from us, and that the farther away you are, the faster it's moving. And if you imagine, imagine that you set off a little explosive just here in between us. And then you took a snapshot of that, a fraction of a second after it had gone off. So your snapshot would show sort of an expanding ball of debris from this thing that had exploded. The things that are the farthest away are the ones that have moved the fastest. Mm-hmm. The ones that are, let's say, half the distance away have moved at half the speed and so on. This is the kind of picture that Hubble saw. He saw things were all moving away from us. And so you extrapolate back in time and you say, everything began where we are. We're at the center of the universe. Yeah. One of the interesting things about this picture, though, is that actually you can build models where this picture applies everywhere in space. At every point in space, everything is moving away from everything else. And that's what the modern Big Bang theory is. So it wasn't just that the universe began at an instant in time. It's actually in these models that space and time have a beginning. There is a singularity in space-time, which is in some ways like the singularity at the center of a black hole. Yeah. And this is actually the origin of time and space.
What do you think? I mean, this is the standard model of cosmology nowadays, right? What do you think of the resurgence of cyclic cosmologies, like Penrose's conformal cyclic cosmology, where the beginning of our universe at the same time is the end of another universe, so that it's, in a sense, it's not really the end, but it's a, continuous series of creations and destructions of universes. What do you think of this?
It would be nice if there were some observable remnants left behind, because then this would become something that we could falsify or we could test. So yeah. I find these appealing. I find it very interesting that, if you look back, for example, at religious notions of the universe, you find some that have a beginning, a middle, and an end, mm-hmm. and you find others that are cyclic. Mm-hmm. And here we are in sort of modern cosmology with a very detailed picture of how our universe began. Mm-hmm. We don't know how the universe will end. Mm-hmm. We don't know if it will keep expanding forever. That's sort of the modern belief. Yeah. Or maybe that's wrong. If it keeps expanding forever, it's kind of hard to imagine how it could have a cyclic behavior.
No, it has
we just don't know. I find these ideas interesting, but it would be nice to be able to test them.
Yeah. I mean, in some of them, at least in this CCC model by Penrose, there is a prediction, not confirmed, but there is he predicts a remnant of the previous universe, right? From something that converted gravitational degrees of freedom of the previous universe would be converted into dark matter degrees of freedom in our universe. But it's far from having been confirmed. Yeah.
I was actually interested in these models. One of Penrose's other predictions from this model is that there's a background of gravitational waves left behind by the decay of particles that he says in this theory exist, called error-bonds. Yeah. And I actually wrote a paper predicting what this background would be, mm-hmm. precisely to see if we could measure it. Mm-hmm. And unfortunately, it would be much too small to measure, right. At least with current technology. Right. But this doesn't mean that one day it won't be.
Yeah. Yeah.
Why don't you start off on the Anthropic Principle, and then I'll pick up. Or you said you're not a fan of it. Shall I do this?
Please, you go ahead.
Okay, so very good. All right. So there's many interesting coincidences in nature. So we were talking about the Big Bang, and it's a little bit hard to understand the Big Bang because there's a characteristic time that's associated with this, and if you try and ask how likely is it that the universe would survive for 14 billion years? You know, either you think it might expand too slowly, in which case it all recollapses because of gravitational forces, or it expands so quickly that nothing happens, that there's not time for elements to form and things like this. Well, there's many details of our universe. If we look at them, we find out that our own existence is somehow tied to that. In order for stars to form, in order for the type of matter that we're made of to exist, certain things in the universe have to be quite similar to the way they are now. Now, one rather simple explanation for this is that, well, we're here and we exist because the universe permits that.
Yeah, it is like that, yeah.
It is like that,
yeah.
Very
yeah.
good.
Yeah.
But then we say, well, perhaps there were many other universes in which we couldn't have existed. Therefore, we observe the universe the way it is because this is the universe in which we could potentially exist. I don't find this personally this is called the Anthropic Principle. I personally don't find it very satisfying because it doesn't have very much predictive power. I don't really see where to go with it.
Yeah.
On the other hand, it's always fun to talk about other intelligent life in the universe and what that might be like.
It's fun. I mean, I think it would be a big advancement of this way of thinking if you could, because there's a lot of talk about how likely or unlikely is the universe that we live in, right? If you could make that way of thinking about it precise and really come to the definition of a space of possible universes with a measure on that space that says we live in a big or in a small part of the space of possibilities, that I would find very interesting. But as far as I know, that hasn't been achieved yet, right? So any sort of assertion that our universe is particularly likely or unlikely is quite hand-wavy at the moment.
In fact, I think the attempts to sort of, there are models, what are called inflationary models of cosmology, in which little child universes form in regions. There's a phase transition in those regions, and bubbles form which expand and become universes. And these universes are basically detached from one another. And so the idea is that perhaps we live in one of these bubbles. The problem is when people try to set out to calculate, well, what are the odds that we would be in a bubble which is like the one that we're in, with properties like our universe, they always seem to come out with 0 as the answer.
Right.
But again, this is a difficult thing to calculate. Okay.
And if mathematics really fits to the universe, means does the universe speak mathematics?
Can I take this?
Sure.
So mathematics is something that's always fascinated me. One of the things I love about it is that mathematical arguments are self-contained. So I don't have to trust, for example, that your instrument is working correctly or that your observations are right. I can work my way through the logic of your argument. For example, if you want to prove that the square root of 2 is not a rational number, it's not the ratio of one integer divided by another integer. The proof of this is something that I can write down, I can work through the details myself, and I come to an understanding which is completely convincing to me. This is one of the very beautiful things about the topic. And for many years, I think until the 1920s, until the beginning of the 20th century, people thought that mathematics was actually an axiomatic system in the sense that you could write down a set of axioms, and from these you could derive mathematical truth. But then a very unexpected thing happened, partly to do with set theory and partly to do with the Incompleteness Theorem. And I think we even have a picture that shows Albert Einstein walking with Kurt Gödel, who is the person who proved this theorem in the 1920s or 1930s. And what Gödel proved is that if you have a system that contains natural numbers, these are the integers, along with arithmetic, and it satisfies a few other, let's say, axiomatic properties about how you can prove things, then this system must contain statements which are true but cannot be proved. And in a way, this kind of kills this initial picture of mathematics as a complete system. but it doesn't remove what to me is the most beautiful part, which is that you can reach logically correct deductions based on your own reasoning. So the fact that mathematics is, let's say, not a complete system in this way doesn't bother me.
Mm-hmm. I completely agree. And one thing that I find interesting also is, I mean, there was the tradition, say, Euclidean geometry, that the axioms of Euclidean geometry, those would be the most fundamental truths, the beginning of everything. And I mean, since then, both in geometry and in all kinds of parts of mathematics, including mathematical general relativity, we found since then that very, very often we find more than one axiomatization of a given mathematical corpus or theory, right? So if you want to say, well, the axioms of a given theory, that's the fundamental, the deepest truths, well, which one then, right? There's different ways to axiomatize a given system and to derive everything from it. So I find, so you could get depressed because of this, because the path to the deep truths is barred. But I find it actually fascinating, right? The idea that you could have different sets of axioms. In a way, it's even more interesting than if there was one set of axioms that would allow you to derive everything. And
I mean, I think, you know, one day if humans don't destroy ourselves, if we live long enough, you know, we might come in contact with other intelligent civilizations, or we might learn how to talk to dolphins, for example. And that will be very interesting because I think that they will share a number of mathematical concepts with us. For example, I think that they will know what the integers are. I think they'll know what prime numbers are. I think a number of things which are mathematical truths for us are things that other intelligent life in the universe will have also discovered and figured out. But it will be very interesting to see which parts of mathematics they have in common and which ones they don't.
yeah, and the ones that are not in common will be just as interesting as the ones that are in common, I would say. Yeah.
Absolutely.
Yeah.
And yeah, let's leave it at that.
Okay.
Okay. Well, thank you very much.
Thank you very much.
That was fun.
Yeah.
Thank you.